So I would like to thank organizer and Dheeraj for two reasons. The first reason is of course inviting me. The second reason is keeping my talk just after the tea break so that people will feel energetic. They will need it in my talk most probably, towards the end at least. Okay. So I'm going to talk about reionization, and since this is the first talk in the session, so I'm going to give a brief introduction. So we know that after the epoch of recombination, in universe entered into dark phases, and then the first dark phase is supposed to be ended when we have the reionization because of the first stars and galaxies form. So there are three main important questions about reionization. Those we want to ask. The first is, what are the sources of reionization? What is the nature of reionization? And what is the timing of reionization? Now, what the other problem that I'm going to talk about today is what makes the reionization a most challenging problem. And here I'm going to argue that the real problem of reionization is not about ionizing photons, but about understanding the recombinations. In order to understand that, let us consider a tail of 3 photons, and let us assume that these 3 photons originate from the same star. Okay? And I'm going to show you a very realistic image of a representation of a galaxy now, in which the star is embedded into the interstellar medium. Okay? So now, the first photon is actually emitted from the star and get absorbed by the interstellar medium. We know that the interstellar medium is highly neutral and very dense. So as a result, the photons will ionize the atom. But then, because of the high density, there is a very finite probability of recombination, and through the electron cascading, you emit the lower and lower energy photons. As a result, the photons will get, the neutral atoms will get, the ionized species will get recombined very fast in the interstellar medium. And this is what we call as a recombination happening within the interstellar medium. The second one is one of the photons actually escapes the influence of the galaxy and goes to the intergalactic medium. It ionizes the gas in the intergalactic medium. But we know that the density of the gas in the intergalactic medium is very, very high. There is a finite probability of and this is and the third photon goes even past the and goes to a very, very large and it fits what happens so as a result, the as a recombination happens in the cell. The second is IgM, and the other is actually highly uncertain. And as it is a customary in astronomy, if it is highly uncertain, we associate a few parameters with one of them. So for example, we don't understand the ISM recombinations very well. This is usually parameterized by escape fraction. When we don't understand about the IgM recombinations, we talk about the clumping factor. And we also don't understand about the Lyman limit systems, how they are distributed in the universe. We typically associate a mean free path, how much a distance a photon will travel before getting absorbed. Okay. Now, the definition of mean free path that I told you about the Lyman limit systems that it traces is actually valid for only post-reionization phase, when the reionization has been done. But during the reionization, mean free path is actually sensitive to the neutral fraction. Okay. In order to illustrate that, let me now show you the maps of neutral fraction for 3 different simulations that I have run. So in this case, you can see that the neutral fraction is slightly larger. Here neutral fraction is less, and it's highly less. And if I compute the mean free path for these 3 models, I get around 3.2 H inverse co-moving megaparsec, slightly higher and higher. So mean free path is actually depends on the clumping factor. Okay, now that's what I want to claim. So first of all, if the clumping factor is large in the intergalactic medium, the recombinations would be large. If the recombinations are large, neutral fraction will be large. If the neutral fraction is large, the mean free path will be shorter. That's what you see over here from this one. And this is very nicely illustrated in the paper by Tirth very recently, that the mean free path is inversely proportional to clumping factor to some order. The other reason is that if you have a large clumping factor and you have a larger neutral fraction, you have to ionize the universe by redshift of 5.3, that is indicated by the Lyman alpha forest. So in order to ionize that, you need ionizing photons, so they should escape the influence of the galaxy, so your escape fraction has to increase. So all these three recombination processes during the reionization are highly coupled to each other. So what can we do about the observation? Of course, escape fraction is very hard to, nearly impossible to measure directly at very high redshift. Clumping factor, because it's a diffuse radiation coming from the intergalactic medium, so it's also very, very hard. And also it's very hard to model because the dynamic range delay for the clumping factor to model is huge. But what we can do is we can try to measure the mean free path. Of course, measuring the mean free path is also hard, but still we can manage to do that. So here is what I'm going to do about how we measure the mean free path in the universe. So what we typically do is we typically do the measurement of the mean free path using the Lyman continuum profile fitting. So we observe some quasars between redshift range Z to Z plus delta Z. You stack the spectrum, all the spectrum together at rest frame wavelength of 912 angstrom. 912 corresponds to hydrogen ionizing frequency, 13.6 electron volt. This is what typically you get when you do. So you can see the typical profile at 3.4 and this is at 4.0 stacked from different quasar spectra. This is from DAISY DR1 and you fit an exponential profile model. Now in order to fit that, you also know that the quasar is a high intensity radiation source. So we have to take out the contribution from the quasar. We also have to take the contribution from the foreground. So when you do that, you get mean free path, constraint on the mean free path. And this method really works very well if the mean free path in the intergalactic medium is much larger than the quasar proximity zone sizes. Okay. So this is going to be the most important plot in my talk. What I'm showing here is the mean free path as a function of redshift, the evolution of the mean free path as a function of redshift. When we do this kind of Lyman alpha profile fitting, Lyman continuum profile fitting, what we see is that there are measurements of the mean free path, something going like this. You can very well fit with the power law using a uniform UV background model. What it means is that all the universe gets ionized at the same time, and then you get something like this, a power law kind of fitting. Now, in the recent year, what we have been trying to do is trying to extend this measurement to higher and higher redshift. And this is what George Baker has done in 2021. He did a measurement at 5.1, which is actually extremely good agreement with the power law. But when you go to a higher redshift, it starts to decrease, the mean free path starts to decrease. As I mentioned earlier, mean free path depends on the patchiness of the reionization. So this was kind of expected, so there is no problem with that. The problem happens because the mean free path also is sensitive to the patchiness of the neutral fraction. So you can ask the question, this will also have an imprints on the Lyman alpha forest. Instead of Lyman continuum, you now go to the Lyman alpha forest. If you take the opacity of the different regions and plot the cumulative distribution function, what you see is that the short mean free path corresponds to more scatter, a long mean free path corresponds to less scatter. So you can use this information to constrain the mean free path. So now you have measurements from Lyman continuum profile and you have from the Lyman alpha forest. So this was the state from the Lyman continuum profile. When you have the Lyman alpha forest, you see a decrease. Okay, so as expected from the uniform UV background. The problem is here. The two measurements from Lyman continuum and Lyman alpha forest, they are actually in 1.2 sigma tension with each other. Now, we thought that, okay, this might be due to the fact that we have a less number of samples. So let us increase the number of samples and see whether we get the same result or not. So in 2023, led by the same group, but the PhD student Yongda Zhu, they did the same analysis, and what they found is that the mean free path is actually very well consistent with the Lyman alpha forest up to 5.5, but suddenly it is actually decreasing with the redshift at 6.0. And in order to explain these things, we turn to the simulations and ask the question whether the simulations can produce this. So we have two kinds of simulation. One is called Aton and Thiessen. What they do is they are calibrated to match the Lyman alpha forest. When we try to match the Lyman alpha forest, we are not able to match the short mean free path. There is another kind of simulation, cosmic dawn 3 simulation, which actually produces short mean free path. But when you look at the effective optical depth distribution, they do not even match. Okay, so you can match either one of them, either Lyman alpha forest or Lyman continuum profile, at redshift greater than 6. Now, this is known as a short mean free path problem in the literature, and this is quite old, like 4 years old problem. Now, you can ask a question, this is just a 1.2 sigma, why should we care? But this is actually misleading because we are talking about the mean free path. But if you convert it into a neutral fraction, there could be a very, very big differences between the two models. The other thing is that because the mean free path is short, the ionizing photon budget has to increase very, very drastically because of this. And in this case, since the reionization is happening very quickly, it has to be very, very rapid and very late, which might be inconsistent with the JWST results that we have. And of course, even if it is 1.2 sigma, this does not discourage IGM community to tell about it could be a new missing physics or something, so they can always claim that this could be a more clumpy IGM or there could be a delayed hydrodynamical response. Okay. So in order to make a progress, what we thought is that we started with doing a new analysis of the Lyman continuum profile fitting. So our approach is not about the fitting, the Lyman alpha line, Lyman continuum profile, but rather to forward model everything and compare the forward model directly with the observations. So here I am showing you two slices. One is correspond to a light cone of short mean free path. This is a long mean free path. You put quasars at the location of halos and extract the long skewers. Okay. Then, because we are looking at the quasar proximity region, so you solve 1D radiative transfer along the line of sight. And then you also do the detailed foreground modeling because the Lyman series is actually a foreground. So we do the full forward modeling and then account for observational systematics like resolution and finite signal to noise ratio or so. So here I am going to show you a sample of some profiles, the stack profile at 5.1. So the green one that you see over here is from observation, and one of the forward model Lyman continuum profile from our simulation is shown by the red curve. So it looks okay. Okay, so I have not done any fitting here yet as of now. So we varied parameters that are related to the quasar properties, for example, spectral indices or age of the quasar. What we find is that there is a mild variation with the age of the quasar. But when you vary the mean free path actually changes the profile quite drastically. And this is a signal to noise ratio variation, so it's a bit, so it happens, it matters to the constraints that we get for the signal to noise ratio. So now I'm going to show you the constraints that we get from the mean free path. So this is what is plotted on the y-axis is the chi-square, plain chi-square, no reduce, but the degrees of freedom for my analysis is 11. So you can also get the goodness of fit if you look at the plot. And on the x-axis is the mean free path. This is what I'm getting now. So you can clearly see a minimum that is happening, and you can see this demarcation line that is there is roughly 1 sigma for this analysis. So if on this plot, if I plot the Lyman continuum profile measurements from the Yongda zoo, what we see is that systematically our best fit values are actually larger as compared to the mean free path that has been measured by the other people using the simple exponential profile. On the same plot, if we plot the Lyman alpha forest, the measurements coming from the Lyman alpha forest, they are actually consistent with the Lyman alpha forest very well. I'm going to show you now the best fit value, how the best fit model looks like when we look at the stacked spectrum. So this is again flux at 4 different redshift bins. This is the observed value. The points here I'm showing you just for the convenience of stacked profile, the bin one. And these are the best fit models. So all these models are, there are 100 models for 100 mocks for single model. And you can see that the black points and the red points, they are very well with each other. If I take the Yongda zoo's points, the Lyman continuum profile, you can see that at the 1.2 sigma, we can actually rule out that measurement very clearly. Okay. So in this plot that we have, the mean free path, previous mean free path model, this was the situation. When we looked at using the new measurements, what we see is that this is consistent with the Lyman alpha forest very well. So what we claim is that there is no short mean free path problem. It's just you need to forward model carefully because the mean free path of the IGM is not as short as not as long as compared to the quasar proximity region. So you have to do a full forward modeling of ray tracing and radiative transfer. And this is my final summary of my talk, where what I said is that understanding recombination process is the main challenge. The mean free path is actually one of the parameter of which is related to recombination that we can actually measure. And mean free path happens to be very short in the literature, but when we compare with the full forward modeling, we see that it is consistent with the Lyman continuum profile. And all of these results actually suggest that the reionization is rather ending late. We don't know when it is starting, but we at least know that it's ending late. Thank you. I'll take questions now.
Thanks for finishing actually early.
Thank you.
Yeah, so Prakash, just to understand what exactly you did, so basically you will put a quasar proximity zone and then...
So, no, I will not put proximity zone. I will put a property of the quasar and then solve the radiative transfer.
So you will put a n dot and a TQ.
N dot TQ, then I will have a spectral indices and all other things.
But where did they go? Are they included in the error bar here?
Yes,
Because there's an uncertainty there.
Yeah. So I included them. So that's why I did not mention it. But when I show this chi-square, it is actually like a marginalized likelihood. So I took into account that thing.
And
Mean free path is free parameter, but I also have TQ, slight dependence on TQ. So that is IGM, correct.
yeah. And
Sorry? No, I want to measure mean free path. I get error from here.
And what is the radiative transfer scheme you are using here?
Okay, so just a one-dimensional radiative transfer. So you just integrate along the line of sight. So the boxes that I am telling short mean free path, those are using Excite ray tracing code because I already have them. No, UVB will change. Okay, so. Gamma H1 is consistent with the ionized fraction that I get, photoionization rate that I measure at these redshifts within the bubble. But outside the bubble, sorry, exactly. That's correct. That's correct. Yes. Yeah. Where to look? Okay.
Thank you for a nice talk. So you have said that the evidence suggests late reionization depending on the MFP. But what about clumping factor and escape fraction? There are still uncertainties. Whether that, if we get more information about those two quantities, will this conclusion change?
Okay, so clumping factor or escape fraction, okay. So this is a bit complicated question. So when we say mean free, we say reionization is ending late. What we mean is that in order to explain the observations, we need a patchy reionization. That means fluctuations in the neutral fraction. That means that means the reionization has not been completed yet. Just based on that information, we are saying that it is late. The clumping factor and escape fraction, of course, they are very, very difficult to measure. So one of the thing that I did not mention about this result is that one of the authors from the Fred Davis has actually tried to constrain the clumping factor using this kind of method, the mean free path method. So when they use short mean free path, they get the clumping factor of 20. That means you get very, very high recombination. If that happens, then your escape fraction has to go very, very high. But because now there is no short mean free path problem now, so you will have a relaxation. So typically the clumping factor we are talking about is 3 to 5. This is a globally average quantity, 3 to 5, okay? But if you look at Keith's paper, I mean, he will know better, you have to have a conditional probability of densities in order to get the local clumping factor. So these are slightly different things. And regarding escape fraction, I'm as ignorant as you are, so I don't know.
Thank you.
Yeah.
Okay.
Yes,
Hi,
yes.
Prakash. Thanks for the nice talk. This is more of an implication of this thing, if there is any. So there was this paper by Villesana et al. Which hinted at a 4.5 kb warm dark matter.
Yes.
Do these understandings change any of those results?
No, I don't think so, because those are done using the Lyman alpha forest,
Yes.
First of all, and those are done at low redshift range 4 to 5, where the reionization has been already over.
I thought they had some data points beyond 5 also, if I remember correctly. But maybe not at this.
No.
So this doesn't change.
This doesn't change. No.
Change the
And I'm ultimately showing this is consistent with Lyman alpha forest, so it will not change.
Yeah, that's true. Okay, thank you.
Yeah, no.
Hi, Prakash. Thanks for a nice talk. I have two questions. One is on the, when you put the quasars and halos at different masses, how do you do the selection? Because there may be a halo mass dependent reionization fraction or escape fraction. So how do you take into account that or analysis?
Correct.
And
So
the
first
second question will be on KZ, because you already have bounds from kinematic Suniav Zeldovich effect from CMB on the weight and kind of the epoch of mid-reionization, how that agrees with your these measurements?
Okay, yeah. So regarding your first question, how do I put the quasars? First of all, okay. So first of all, we have a completeness limit of our sample for halo mass function. So we typically put about 10 raised to 9 and 10 populates with halo. Now I do not have an escape fraction as a free parameter in my model at all. I just assume that they just radiate and then they get the mean free path. So I am interested in the what mean free path they carve out. So escape fraction naturally, if I have to calculate it from my thing, if the mean free path is short, my escape fraction will automatically be reduced. But I'm not interested in actually tuning my parameter. Yes.
And is this quantity halo mass dependent, the mean free path?
No, it depends on the clustering of the halos. Because when you say the reionization is going on, what happens is that it's the property of the how the halos are clustered that drives the reionization. Individual halos will not have any contribution. And I do have a plot, may not be here, but I can show you that it depends on the clustering.
Because
of
the
the halos.
gas fraction will decide in the halo. If there are more clumpiness or gas fraction, the amount of photon that can actually come to IgM is less.
Yes,
That will have an impact.
correct. True.
We can talk about this.
Yes.
What about the KSZ part?
KSZ part, okay, I'm not much expert on KSZ part, but what I can tell is that the models that I showed, they are ending, so they have a late ending reionization. I cannot tell anything about the midpoint of reionization. So what happens is that even if the midpoint of reionization at say 7 or 7.5, it does not matter for the Lyman alpha forest because it is ending very less. And the neutral fractions that I'm talking about here is less than 0.1. So Lyman alpha is a resonant transition, so it's a bit complicated to say. Yeah.